All right, question number 1 was a question asking you to interpret dummy variables. This was just a reshuffling pretty much of what we had done in the early part of the class, where we had completed schooling and income categories. In this case, I omitted the second category instead of the first category. You know, if you've got a bunch of dummy variables, you can't include all of them because the things would blow up. You have to omit one of them, and then the remaining coefficients show deviations in the value of the dependent variable adjusted for the covariates from that omitted category. So in this case, the omitted category is $15,000 to $25,000, and the first question is just the interpretation of this 1.21 coefficient, and most of you understood that that was the additional years of education associated with being in a family with a family income of greater than 35,000 relative to a child being in a family with income between 15,000 and 25,000. It's always relative to what? And in this case, it's always relative to the omitted category. Second part is to describe the relationship. So people struggled with this. What we know is that if instead of having a continuous income scale, we just have categories, right? And one category is this less than 15 category. Then we have a 15 to 25 category, then a 25 to 35 category, and then we have a greater than 35 category. Right, so it's not a continuous scale, it's just four different categories. And what we know is that the coefficient for being in the lowest income category is minus 0.82. So if you think about this as a bar graph, right? It's coming down about this far, right? This is the minus 0.82. And then because 15 to 25 is the omitted category, you know, that's just at 0. That's the reference category. 25 to 35 is 0.6. 0.60. And then being in this more than 35 category goes up to 1.21. Okay, so that's what the numbers mean in terms of categories. If you think about this as a categorical variable consisting of 4 categories, this is the bar graph that you get, right? But if you're asked, because this is an income categorization, you're asked to describe the relationship between years of education and income, right? Income is a continuous variable, it's not a categorical variable. And so what we want to do really is go from a bar graph to a scatter diagram, right? We want a scatter with a point that is minus 0.82 on the y-axis. But on the x-axis, it's not, you really want to know what the income value associated with this lowest category is, right? So if you take all the people with incomes less than $15,000, what is their average income? And so here, looks like that, except instead of categories, I've got income as a continuous variable here. So we know that there is one point that corresponds to an average income for every child under $15,000. If you think about an income distribution, it's kind of a normal curve. It's actually a log normal curve because there's a very fat right-hand tail. So, the people less than 15,000 is going to be something like the average of these people on the curve. And that's probably not going to be halfway between 0 and 15. It's probably more like 2/3 of the way. You don't have to know, these kind of exact things. But if I were to associate an income, an average income, I could calculate it, obviously, if I had the data. For less than $15,000, it'd probably be about 10,000, right? So what we know is one point on this graph is going to be, if this is 10, 10,000 is associated with minus 0.82. All right, so that's one point on the relationship, a continuous relationship between income and years of completed education. We know exactly about the second point. Well, we have to guess at what the average income is between 15 and 25. And that's probably going to be about halfway in between, 20. So at 20, we've got a 0. Now, if we go up 25 to 35, again, the average is going to be halfway in between, about 30,000. So once we get up to 30, we're up to 0.6. All right, but now, and this is the tricky part. If you go back to the lecture where I think it's week 2 when we talked about dummy variables, I talked about this exact problem, right? So you can go back and look at that. But the key issue is, if we're trying to plot the income associated with this 1.21 years of education increase, it's going to be, the average income of kids living in families with incomes more than $35,000. And if you think about the income distribution, the average income in the population is about $60,000. But the average for people with incomes above 35,000 is going to be even bigger than 60,000, right? It's kind of the average of this distribution beyond 35,000. And it might be, let's say, 70,000. So again, you don't have to know that number, but you have to understand that you're trying to convert a bunch of categories into a continuous distribution. So you have to know what the income is to associate with the more than 35K. And it's probably, around 70,000 or so. So we get 1.21, something like that. All right, so you've got 4 points in the distribution, and you want to be able to describe what the relationship is. And there's some eyeballing here, but you're going up very quickly at first, and then you're going up more slowly, right? And remember, when we talked about the various functional forms, the one that fit pretty well was a spline function, right? That was very steep up to 20,000. And then after that, it was much flatter. So what we have here, is a function that looks kind of like that. You don't really know what these points are. You just know 4 points. So I didn't do this very well. So we want to be able to connect. So this is really steep at first. And then it flattens out really quickly, something like that. Sorry. Okay, but the key here is to know that you're going from a bar graph essentially to a scatter point graph. And what you know from the regression are really 4 points on this continuous relationship between education and completed years of schooling. All right, so can't ask you questions, but if you have questions, please talk to me about them. Third part of the question, how would you go about testing for whether the coefficient on the 25 to 35 is significantly different from the more than 35? All right, so we just want to do something that gives us that in as simple a way as possible. And the easiest way to do it, here in the setup, we had omitted this category. So this was the years of education associated with being in 25 to 35 rather than 15 to 25. So to get a comparison of these two, the easiest thing is to omit either this or this, and then include this again, and include this as before. All right, so then we've got a dummy variable for less than 15, a dummy variable for 15 to 25. Let's say we omit 25 to 35, and then we include the more than 35. What are we going to get for the coefficient on more than 35? We're going to get a number that represents the years of education difference between kids with incomes more than 35,000 relative to the omitted group, and the omitted group is 25 to 35. Right, so you get a coefficient and a t-test. You know, the coefficient's going to be 0.61, just the difference between these two. It's hard to know exactly what the standard error is going to be. You've got to do the run to get that. But it really couldn't be simpler. You do a somewhat different form of the regression command and just look at the coefficient on the, in this case, the greater than 35. If you had omitted this one and included this one, then you'd get coefficients that are negative all up here. Everyone's completing less school than here. And this would be a minus 0.61 with the same standard error and the same significance value. So that's the easiest way to do it. Well, actually, the easiest way to do it is you can take the original run and just have Stata do a test for whether 25 to 35K equals more than 35K. Right, so if you start with the original regression, you've got 1, 2, 3 variables included. This is the omitted category. If you just do a test on these two, the equality of these two, it's going to test for whether this 0.61 difference is significant or not. And the kind of significance level that you get from that test is exactly the same, you should try it, as the significance level if you omit this and look at this coefficient, or omit this and look at that coefficient. So two pretty straightforward ways of doing that test. All right, let me set up number 2. All right, question number 2 on the midterm exam. This is a logistic regression question. There are several ways of getting a regression out of the dichotomous dependent variable. The simplest way is a linear probability model where you've got a 1, 0 variable on whether some outcome, in this case, all right, high school completion. So 1-0 high school completion is some function of X variables. We said that gave predictions outside the range and had heteroscedasticity. So people have come up with several different transformations of a probability that have better properties. In other words, don't give predictions beyond the 0-1 range. The most popular is a logistic regression, right? Where it's the log of the odds as the function of the independent variables. If you exponentiate both sides of this regression, you get e to the log p over 1 minus p. So this b1 isn't the same as this b1. I want to make sure people understand that. But the form of it is not the log of the odds, but rather the odds ratio itself is a function of some variable, set of variables. And then finally, because the interpretation of a linear probability model is so much better, you want to jump right to a change in the chance of something happening, like completing high school. It's easier for people to think in terms of probability change than in terms of odds changes, or certainly log odds changes. So another useful step, if you do use a log odds logistic regression approach, is to take the results and then derive what the change of probability is at some point in the distribution of your independent variables. And what Stata will do for you is allow you to plug in whatever values for independent variables you want to evaluate this change at. Remember the logistic function itself. If this is high school completion, and this is, this is motivation in 8th grade. That was the example. All right, and we've got a bunch of points that are either down at 0 or up at 1, and we're fitting some kind of, actually, high school completion ought to be higher for motivation being higher. So we're fitting some kind of S curve. Its slope is changing everywhere. So if we want to know about a change in probability, in other words, if we want to know about the slope of this logistic function, we have to tell Stata where we want that slope evaluated. And the default in Stata is just to plug in the mean values of all the independent variables. But you can do whatever you want in terms of asking where to evaluate this. It will tell you what the change in the probability is. Margins also gives you something completely different, which is a predicted probability once you plug in independent variables. And that was the source of confusion that people had. This was part B. And I ended up thinking, this isn't a test on Stata, it's a test on statistics. So I thought, given the confusion, we'll just throw it out and not grade it. So that's why that was the one that was thrown out. But part A, interpret the meaning of the 1.00 coefficient on the motivation variable, right? So here we've run a logistic regression and obtained a coefficient, if this is motivation, of 1.50. And the question asks you to interpret that. And the interpretation is for every 1 unit change in motivation, we have an associated change in the odds of completing high school of 1.50, which means that the odds are 50% higher if motivation increases by 1 unit. right? So in contrast to a kind of a normal regression we're used to thinking about, the base isn't 0, the base is 1.0, even odds. So we want to know whether changes in motivation are pushing those odds above 1.0 or below 1.0. And when we get a coefficient like 1.50, that's saying instead of 1, it's 50% higher than 1. So the odds are being increased by 50%. Okay, and the final part C, said if you have a linear probability model and a coefficient of 0.067, most of you got this. This is a 6.7 percentage point increase in the probability of completing high school. All right, so in a linear probability model, we aren't fitting some fancy S-shaped function. We're just fitting a straight line. And the slope of that line is going to be B1. In this case, 0.067. So every unit change in motivation is going to be associated with moving 0.067 percentage points up this line. And it's linear, so that 0.067 is constant all the way up and down the motivation scale. That's just the assumption that the linear probability model makes. And what I'd hoped to do in part B was to get a similar kind of percentage point interpretation off of the log function, the logistic function. And that was my 0.089. So what you usually find when you compare a logistic result to a linear probability result, you get some differences. It depends on where you do the evaluation of the change in probability. In this case, it was instead of 0.067 percentage point increase, it was 0.089 percentage point increase. And that's all very, very different from this odds ratio regression, where the coefficient that you get has no direct probability change interpretation. It only has a log odds or an odds ratio change, 50% in this case. So you can back out what the change in probability is, but it's giving you a change in the odds. And then if you were to run a log odds version, the coefficient would tell you what a 1 unit change in motivation does to the log odds of completing high school, which is a very difficult thing to try to get your head around. All right, so let me pause and set up questions. Okay, let's do number 3 now. This mixed together a couple of rather different questions. I wanted to make them all count the same so that I could omit one of them and give you a break until Paul said, no, let's do all 4. So anyway, they're combined. So somebody told Paul, right? I don't know who it was. I told Paul he owed me one, so we'll see what he comes up with. All right, first question is, why is it convenient to center the key independent variable driving the discontinuity at the point of the discontinuity itself? All right, so let's think about that in the context of double dose. Double dose algebra in 9th grade took everyone below the 50th percentile in terms of their 8th grade math scores, gave them double dose, right? And it wasn't 100%, and there are complications, but by and large, many, many, many more people took double dose if they had 8th grade math scores below the 50th percentile as opposed to above the 50th percentile. So the regression, as we've talked about, is, let's just say we take the 11th grade ACT math score as an outcome. It's going to be a function of 8th grade math. This is percentile abbreviation. 8th grade percentile plus, and this is the double dose, whether their percentile was below the 50th percentile, in other words, whether they were double dosed, plus the interaction of 8th grade percentile times whether they were double dosed. And that works because it's going to fit two lines with different constants and different slopes. For the non-double dose, that's going to be 0, that's going to be 0, and you're just left with A plus B1, the 8th grade percentile. So this is the slope for this is the line for the non-double dosers. It has a constant back here at 0 percentile and a slope of B1 in this case. And then for the double dose people, let's say that they are on a trajectory that's more rapid and continues. So by the time you get up to the 50th percentile, this isn't a trajectory, this is going up the percentile. So you're gaining your 11th grade math test if you're double dosed, all the way up to 50th percentile, the higher you were on 8th grade math. And then once you get beyond the double dose qualification, then you drop down and continue at a slower slope, right? Nothing guarantees that that's the case, but let's suppose that's the case. With this equation, you're fitting two different lines and they can have any slope or any intercept. But if this is the case, then instead of an intercept of A for the double dosers, you're going to get A plus B2. In this case, B2 is going to be negative. So the intercept is going to be down below A. And then you're going to have a slope that instead of B1 is B1 plus B3. Right, so B3 tells you what the difference in slope is going to be. So the question asks, why is it more convenient, instead of putting 0, the constant, way the heck out here, why not put it, in this case, in the very center of the data at the point of the discontinuity? In other words, we're transforming this scale from 0 to minus 50, minus 25, 0, plus 25, plus 50, right? These are still percentiles. They're still going up 100 percentile units. But instead of going from 0 to 100, we're going from minus 50 to 50. And we're centering this right at the point of the discontinuity. So instead of the A constant for the non-double dosers being way back here, a projection back to the 0 percentile, it's right at the discontinuity, right? So A is this amount. And then B3, I'm sorry. So A gets adjusted, the constant gets adjusted by B2, right? That happened over here. B2 is negative, but now B2, this is A plus B2 again. But now B2 tells you exactly what this gap is. In other words, to what extent at the discontinuity, where it's really the population, this average local treatment effect, where you're doing the heart of the analysis, because that's where the kids are most comparable, 49th percentile, 51st percentile. So the jump here tells you what the impact of double dose is for 8th grade math in this case. And the jump is B2. So instead of B2 having this weird kind of negative interpretation over here because you were projecting it back to the 0 point, here you've moved the 0 point to center at the data, and B2 becomes exactly the number that you need to show you what the impact of double dose is. All right, if you have any questions about that, you can talk about it maybe at the beginning of the next live class we have a week from Monday. The second question had 2 parts, and it just said, suppose you've got y equals a plus b1x, and y and x are in raw score units. So B1 is equal to a change in the raw score units of y relative to a 1 raw score unit change in x. And the question is, how would you go about converting this B1 into a standardized coefficient? In other words, you want a standardized change in y relative to a 1 standard deviation change in x. And the two, so in week 3, I think, I put in a link to this handout that kind of explains all the ways of transforming coefficients. One of the transformations into a standardized coefficient from raw score coefficients was this B1 times the standard deviation of x over the standard deviation of y. Why is that the case? Well, if what we want to do is go from a change in y to a change in the standard deviation units of y, we divide delta y by the standard deviation of y, and similarly for x in raw units, we want to divide by standard deviation of x, and that ends up being exactly that if you invert and multiply. So that's probably the easiest way to do it. Just do a run and find out what the standard deviations of x and y are, get their ratio, and just multiply it times the raw score coefficient that's coming out of your regression. Another, a bit more cumbersome way to do it is to standardize x and y before you run the regression. In other words, you could z-score x and y and then run the regression. Which will then give you a different coefficient. It'll be a standardized coefficient. It'll be identical to this standardized coefficient, showing the change in the standardized change in y associated with a 1 standard deviation change in x. You can also get data in running a raw score coefficient to just give you what the standardized coefficients are. And it will be the same thing as well. All it does is do this kind of standardization. Okay, let me set up number 4. All right, moving on to number 4. This gave you interaction regression that might well be common in the research that you do if you want to look for group differences in some sort of relationship. You create a dummy variable for the group, in this case, whether Hispanic, and then run a fully interactive model, right? So you start out with the basic model, constant age and age squared. You want to know what the relationship is between age and task value across middle school in this data set. And you want to allow for the fact that that relationship may differ. This allows for a difference in the constant. This allows for a difference in the age term slope, and this allows for a difference in the age squared term slope. So you're probably going to see a lot of equations like this, maybe in your own work, certainly in the literature. And it's very important to be able to understand what these numbers mean. And I tried to simplify things. I wanted you to both show that you understood what a dummy variable interaction model was, as well as what a quadratic was. So I tried to simplify things by saying, all right, let's take non-Hispanics and make sense out of the quadratic, right? And for non-Hispanics, this term is 0, this term is 0, this term is 0. So you're just left with task value is the constant minus 12.45 age plus 0.49 age squared. And all of these questions are about non-Hispanics, so they are based on this, this equation. And the first question was, how do you interpret the minus 12.45? Well, we showed that coefficient on the, in this case, age term is the slope of the function at age equals 0. Right? We took the derivative of a task value with respect to age, and we just got minus 12.45 plus 2 times 0.98 age. So solving for age equals 0 just gives you this as a slope, and that's the slope at age equals 0. So going from the point of birth, I mean, it's clearly ridiculous because we're, if you centered the age variable, it'd make a lot more sense here. But in this case, if age is going to run from 10 to 15 in the sample, this is projecting all the way back to 0 age. So this minus 0.45 coefficient tells you how much you're changing, how much the slope is changing at 0 years of age. So that was the answer to that. The second question was, what's the shape? Is it an inverted U or is it a U? And to determine that, all we have to do is look at the sign on the squared term. If it's a plus sign, that implies a U shape. If it's a minus sign, that implies an inverted U shape. So the answer in looking at this, just look at the sign, you know it's got to be a U shape. And then the third question is, at what age does the age task value relationship have a 0 slope? Now, we're really talking about something that's this is age, right? So 0, let's say 5, 10, 15. The task value scale only runs from 0 to 5. So the intercept is 81. So we're talking about a function that, is coming down from way up here. The relevant age range for the sample is here. So we're fitting this line that is parabola that's looking something like this. But the slope of 0 is going to be minus b1 over 2b2. All right, if you go back to the lecture where we talked about this, it's just getting this derivative and solving for where the derivative is 0. Minus b over 2b2 is going to be minus a minus 12.45. In other words, plus 0.45 divided by 2 times 0.49. And that is about plus 12.7.